Thanks. Now you should be able to see my screen.
Yes,
so,
it looks good.
Yes.
Okay, good. Thanks for confirming. So thanks to the organizers for inviting me. I was hoping to give you a less virtual tour of our observatory, but I hope it will nevertheless be interesting for a lot of you. One of the main points of the motivation for the Pierre Auger Observatory is the study of the ultra-high energy cosmic rays, which is the energy range really above about 10 to the 18 or 10 to 19 electron volts. It depends a bit on what you want to, what you count as ultra-high energy. This is in a range where center of mass energies are larger than that of the LHC, so it also has a particle physics impact, obviously has an astrophysics impact. So you see here at the spectrum of the cosmic rays, we are studying the very end. The LHC would be roughly here, so somewhat below the range we can study. This slide hasn't been updated for a long time, and the reason why is the bottom two parts, the acceleration mechanism and the sources, we can't really study yet at the highest energies, even though we have hints and many theoretical ideas because of the low flux. If you get really to the very end of the spectrum, you have to fight with the low flux, and show you a spectrum later on, of having about one particle per 100 or 1,000 square kilometers and year. That makes it very difficult, and it requires a bigger observatory, and it makes actually the Pierre Auger Observatory way too small for what we wanted to do. So that's sort of like the big motivation. If you look at the collaboration, the Pierre Auger collaboration has 17 countries, about 460, 450. This oscillates a bit in collaborators from 17 countries. This slide needs a minor update. Colombia is full member by now. So you see we have an active Latin American component. Argentina, Brazil, Colombia, Bolivia, Mexico are all participating, with US and a number of European countries and Australia. So if you look at the observatory, it is in Argentina, in the border between the Andes, more or less on the line connecting Buenos Aires and Santiago de Chile. It is an area of 3,000 square kilometers, which I said is still too small. The dots here are the 1660 surface detectors on a triangular grid of 1.5 kilometer spacing, with an extra infill area here, higher density, which has 750 meters spacing, where we're also adding underground muon detector. It has here 4 fluorescence sites around it, with 6 telescopes on each side. And on one side here, you see the heat. It's an extra 3 telescopes which are elevated to be able to study nearby lower energy showers. So we have a total of 27 telescopes, which cover more or less the full surface array. But they have been able to also work as stereo detections, up to the fact that at highest energies we've even seen in the central region quadruple events seen by all 4 telescopes all 4 sites at the same time. And we have lower energy extensions, heat, and the infill is part of it. And we have in this area here where it says IRA, radio detection experimental testing site. If you want to give the observatory characteristics in a nutshell, you would call it an air calorimeter with an surface area of 3,000 square kilometers and about 2.5 times 10 to the 10 tons. The mass is important when you're looking at low cross-section particles like neutrinos. A single surface detector station looks like this. They're really isolated in the Pampa Amarilla, and they consist of the water tank of tanks, container with 12 cubic meters of water, 3 photomultiplier tubes to detect the Cherenkov light, electronics enclosure, batteries, solar panels, so they're autonomous, and 1 antenna for communications and a GPS antenna for timing. And this gets complemented by the fluorescence detectors. So this is one of the fluorescence detector sites, where you see here the shutter doors for the 6 telescopes in the site. You see a LiDAR for atmospheric monitoring behind, and the comms tower. The round dishes are the microwave background, and what looks like you run-of-the-mill cell phone antenna. Those are the antenna that communicate to the tanks to the Cherenkov detectors in the field. Inside, the telescopes are Schmidt telescopes. They have a filter, which is at the same time a band filter to limit to UV, where we get fluorescence light with a corrector ring around to get a larger aperture than we would normally get from Schmidt telescopes, a spherical mirror, which is typical for Schmidt, and a curved camera with 440 PMTs. So that's the fluorescence part of the detector. Now, how do they work together? The ideal is to get hybrid events that we detect with surface and fluorescence. Those are our best events because we have multiple bits of information. The problem, though, is that fluorescence detection only works about 10% of the 10 to 15% of the time in moonless, cloudless nights. Or moonless meaning low moon, like about a week of the month we can't really see because there's too much moonlight in the sky. So we have only a small fraction of these good events, and we complement this by using the surface array for the statistics. And an interesting thing is we can use the fluorescence detector to calibrate a number of our surface detector observables to have less fluctuations or less dependent on Monte Carlo. Particularly interesting is here the example of energy determination. The fluorescence detector is pretty much calorimetric up to some missing energies that goes into neutrinos and muons. The area under the curve where you just look at the number of particles that in the cascade, which is basically the equivalent to the number of fluorescence light that gets emitted because the charged particles ionize the atmosphere, which then at recombination emits fluorescent light. That area under that curve corresponds to the energy. So we don't need Monte Carlo to calibrate that once we have an idea of what goes into missing energy. And from that, we then calibrate our surface detector variables. We use a signal strength at 1,000 meters from the impact point of the cascade, from the shower core, to estimate the energy from the lateral distribution on the ground. And we use similar techniques to calibrate other SD observables, always comparing an FD observable, which you can typically measure with more quality, to an SD observable, which would normally depend on simulations, but then by calibrating it with an FD observable, we get a more robust result. To get really to an energy estimator, we use some which is the constant intensity cuts, where we assume that cosmic rays are first order isotropic, so we would expect for the same energy, the same flux irrespective of the direction. So, but the attenuation in the atmosphere means that we have a zenith angle dependence, and this is the constant intensity cut. We just say at different energies we have the same flux in the. So we use that to say different points along this curve corresponding to different zenith angles here give us should correspond to the same energy, and this allows us to connect signal on the ground to energy. And then we bring it to a reference angle, which we use the signal at 38 degrees, because that's the average weighted by solid angle in the sky. for a detector that has an observing window from 0 to 60 degrees. And so we derive these curves from observation and verify them with simulations. And then at the end, so these curves allow us to connect the observed signal at an arbitrary angle to a reference signal at 38 degrees. And then we can compare this to the fluorescence energy. And you'll see here we have a fairly good linear correlation, obviously worth statistics at the higher end and with a very limited spread. And what is important here in this curve, there's no bias depending on the primary energy, on the primary particle. We get the same calibration curve that works for proton or iron primaries going to the two extremes of where we expect cosmic rays. So this makes it fairly robust. And we can use the same technique to calibrate other variables. If we use the infill array where we have 750 meter spacing, we use 35 degrees as a reference angle. If we use very inclined air showers, which we can also detect, we basically only get muons on the ground. The electromagnetic part of the cascade is attenuated. So we use as a reference the muon density on the ground at 10 to the 19 electron volts and calibrate to that. So you see basically the same curve that works at all energies. And this allows us to construct a combined spectrum. The infill, the 750 array, allows us to go to lower energies. The inclined showers allows us to get more statistics. And this is a spectrum that just got published about 2 or 3 weeks ago in our publication. So this has a bit more features compared to the previous spectrum that I used to show a couple of years ago, for those who might remember. We combine the results from these different detection techniques. The two graphs contain the same spectrum. In the first top graph, you see the number of events in each bin. The difference is that in one case, spectrum is multiplied by e to the 2, in another case by e to the 3 to take out the dominant feature. If you look at the spectral indices, they're all around e to the -3. So by multiplying with e to the 3, we get a relatively flat spectrum where you can really see the feature. First, an index, spectral index above 3 in the first region, below 3, which looks here as a rise in this region 2, something which is fairly flat and index around 3 in the region 3, and then a very steep cut of a spectral index of about 5 in the higher region. The transition are at about 5 EeV from 1 to 2, at about 13 EeV from 2 to 3, and then the cutoff at about 46 EeV, which is roughly 10 to the 19.5 or so, which corresponds to the famous Greisen cutoff energy, but it can also be a cutoff due to acceleration running out. You see here the combined fit function we use, which is just set like this, so we have smooth transitions instead of putting a broken straight line fit there. What is interesting, what one can do with this is take not only the spectrum, but combine it with other information like the maximum of the shower development, which you can see in the fluorescence detector, make some assumptions, and then construct a model or different models to see if we can say something about possible source populations. This has not been updated completely, simply because the graphs from the older publications are nicer. If you look at this, you see in a fit 2 minima, you see this here in the cut along the dotted line more clearly, which would be the 2 best fit models. The interesting thing is that those models have different property. If you look at the first model and you look at what would you expect, the A equal 1 is the hydrogen, the proton, then you have a light, helium and light elements, the mid-range and the upper range, but no A equal 56, so there's no iron in this particular fit. That is one possible model or another model, which is a model which is proton dominant. You see the A equal 1 goes up to the highest energies, and the other elements just support this from below. They're both acceptable from our fitting. At this point, we do not claim that we've understood the sources. We've shown that you can do this kind of fits. The first minimum is somewhat extended, that makes it hard to fix values. The second minimum is well reproduced, but has many more protons than we expect, than we see in our data, where we have an indication of a heavier spectrum, of a heavier composition at high energies. The preferred model has a lower cutoff in the source. So this is the hint which I mentioned, that the cutoff in the spectrum might be partially to a source cutoff and not only to cutoff in the propagation, where the universe becomes opaque for protons or for nucleon due to proton, photon, or nucleon photon interactions that break up the cosmic ray with a very high inelasticity. And we have an indication of a mixed composition which conflicts with some models which prefer pure protons. Another interesting result, which was actually in 2017 listed as one of the top 10 breakthroughs, is the Rayleigh analysis in Right Ascension, which indicates if you do a multiple composition of your cosmic ray distribution and account for non-uniformities in your exposure, that you get a non-zero amplitude for the first harmonic and the phase which is around 90 degrees. And this is a result, this is why it was important. It's a 5 sigma detection of the cosmic ray anisotropy. Having 5 sigma detection in cosmic rays is very rare. This is why it was labeled a breakthrough in that year. You can see here the dipole. You can see you could try to fit also a quadrupole to it. It's no longer so significant if you add the second harmonic to it. This is all for energies above 8 eeV. We have now, first the position of the dipole points away from the galactic center, which I show in a moment, and is more or less in the direction where we have concentration of masses in one of the galaxy catalogs. It is the offset between the dipole direction in the catalog and what we observe is more or less compatible with the assumption that we have a few particles between 2 to 5 eV that get deflected in magnetic fields. So this means it's consistent to assume that it's normally just galaxies that are the source population. But it's not, it's a hint, it's not a proof. The dipole is the thing that is really there. We've been recently analyzing this with more statistics and look at this in detail with the amplitude and the phase. The gray band corresponds to this greater than 8 eeV range that I mentioned before, where you see very clearly an amplitude that is different from 0. Most of the other points, if you look at here, are upper limits or much smaller, and you very clearly see the phase turning away from the galactic center to the outside as you go from much below 8 eV to the 8 eV range. You can also look at this if you look at where the particles are pointing at different energies. Here, the right square is a blow up of the central region. If you look at it, so what it tells you is at lower energies, so on the right square, all of them are more or less compatible with pointing into the direction of the galactic center, and this is also directions of where IceCube and IceTop here indicated by ICIT see some signal. If you look at it, the yellow circle here corresponds to the yellow circle on the left plot. The green circle on the right plot, the biggest one that you see, is the blue circle on the left plot. But you see that as you go to higher energies, which is the green, purple, and then the gray circles, you clearly move away from a galactic center direction as you go to high energies that are here analyzed, which is again the indication that I mentioned that the dipole is not in galactic origin. You would expect the preferred direction from the galactic centers simply because we are off center. So if something is got, if particles, if the acceleration of cosmic rays happens in our galaxy, you would expect a dipole in the direction of the galactic center because the Earth is off center. So you have on the average more mass in the direction of the galactic center than away from it. That's all that's behind why we can interpret this dipole as indicating that the highest energy cosmic rays are not galactic in origin. So another, I find exciting possibility of what we can do with the observatory is neutrino detection. So how can we see neutrinos in an observatory that is not underground? We use the atmosphere as a shield. If you have to think of this plot here of these graphs as being turned by 90 degrees. If you have a normal air shower, this line would be pointing more or less from the vertical down, and you would see the air shower here. You would have the most active region where particles get emitted, and then depending on where they're emitted in this region, they're emitted as circles they arrive on circles of different, or spheres of different radius, simply because all the particles emitted from here would correspond to the inner shell. The particles emitted from there have further to travel, so that all traveling at the speed of light would give you a larger shell. So, and if you look at this, what you see is simply, if you're close to the center, the two shells are pretty much coincide, which gives you short signals. Further out, the shells separate, so you get more extended signal. If you go much, much further from the active region, this effect gets less, and you see all signals fairly short. So this is something that applies to normal air showers. Now, what happens if you do it for very inclined showers for neutrinos? So the ground now, instead of being in the vertical, would be very inclined. And if the shower happens deep in the atmosphere, which would be the indication of a particle with low cross-section like a neutrino, then you would have the early part of the shower, which intersects in a region where the shells are more separate, so you get longer signals. The later part corresponds to a region where the shells are closer together, and you get shorter signals. So you would see the difference between long and short signals as a function of early and late signal, not as far from the core and close to the core. That would be one of the ways to identify neutrinos. A different way of looking at it is if you look at inclined showers, it's not only the neutrinos that produce inclined showers. You also get simple hadronic shower. Nothing prevents a cosmic ray from coming down the atmosphere at 80 or 85 degrees. But what happens for a normal hadronic air shower, it would develop very far from the atmosphere, from the detector. The electromagnetic part gets absorbed, so we get what we call an old shower, which is basically muons, which gives us short signals. The neutrino shower it doesn't have to, but can have its first interaction closer to the detector. If that happens, we can tag it by having what I showed in the previous slides, extended signals at the beginning with an electromagnetic signal and short signals later on in the shower. We can have, because of the low cross sections of tau, relatively low cross section of tau, actually upwards going showers where the tau converts in the rock, and the tau neutrino converts in the rock underground, creates a tau that can travel actually quite long distance through the rock, leave the Earth, and then decay above the detector, creating again a shower relatively nearby, which we can tag, but which would come at 91 or 92, 95 degrees from the ground. A way to understand the difference between the first two is also to realize that one atmosphere, which is about 1,000 grams per square centimeter, corresponds to a distance of about 10 kilometers at 90 degrees. As a reference, the diameter of Auger is about 60 degrees. So what you can see in very inclined showers, which we have, which extend some 30 degrees or more, we can see that the shower ages along the footprint. This is exactly what happens here in this middle plot. So what you see is what I've mentioned. You get the slow broad signal for the electromagnetic and the fast narrow signal for the muons. So if you have a shower that combines both types of signal, that would be a neutrino induced shower, or as a caveat, a shower induced by any particle with a low cross section. But the only particle we really know from the standard model is the neutrino, so we use this for neutrino tagging. And from there we can establish neutrino limits. And what you see, there is an energy range here in the around 10 to the 18 to 10 to the 19 electron volts, where the Auger limits are the strongest. At lower energies, the best limits come from IceCube. At very high energies, Antares has the best limits. The other important thing, what you see here, is number of these observations really enroach or even cross the Waxman-Bakal bound, from assuming that GZK interactions, proton interactions with, assuming that all cosmic rays are protons and they would interact with the GZK cutoff in the GZK mechanism with photons from the cosmic microwave background, you would expect a certain production of neutrinos, which would be what people call the guaranteed neutrino flux. We're seeing that our limits are below that, which is not incompatible with a theory. It simply says that what the cosmic rays at highest energies are not all protons, which is consistent with our observations that I'll show you later on. But you see that there's a number of the models that are pointed out here are really getting ruled out by the limits we can establish. We have only limits so far. We haven't seen a neutrino, unfortunately. Another thing we can do is do photon tagging. Photons are much easier to identify than the separation between heavy and light nuclei, because they have only electromagnetic interactions. They have smaller cross sections, so the maximum of the shower would be deeper in the atmosphere. They take longer for the shower to develop and enter. So compared to the shower maximum that we observe from hadronic showers, which is the data shown here, not just for Auger but for other experiments, photon showers would be above. The structure at the top, now first two features, the separation goes larger because the LPM effect at high energies suppresses electromagnetic interactions. But then at the very high energies, you get pre-showering that a high energy photon can actually split in plus and minus in the magnetic field of the Earth. So you get actually the first interaction happening not at the top of the atmosphere, but before, and you would get several lower energy particles hitting the atmosphere, which would then initiate showers early on. This is why you have this slightly complicated structure at the highest energy, which also means you have to model very carefully if you want to do correct photon tagging. You can also do photon tagging with the surface detector. It's again based on the same observation that photon-induced showers penetrate deeper into the atmosphere. And this shows it up in two surface detector observables. One is the curvature of the shower front. If a shower gets deeper in the atmosphere, the same which I mentioned in case of neutrinos, the the curvature has to be larger compared to a shower that gets higher in the atmosphere. And you get a timing difference, which manifests itself as a signal rise time or the signal width. If you look at these two triangles here, you have the time for the first particle that leaves the shower axis towards your detector versus the time of a particle that follows longer with the shower and then in a later interaction gets sufficiently large transversal momentum to get to the shower. And it's clear the red line is larger than the blue line, but if the triangle collapses, it gets more degenerate, this difference gets smaller. So a particle high up in the atmosphere will have smaller difference and therefore smaller delta T compared to a shower that develops lower in the atmosphere. With those two variables, you can get a fairly clean separation in this two-dimensional plot. You see, if you compare here the gray squares, which are hadronic simulations, with the crosses, which are photon simulations, that you see a clear separation of the two blobs with a few hadrons entering some of the central part of the photon regions. But if you put a cut sufficiently strong, you can really avoid contamination of your photon sample with protons, which would be the hadrons that fluctuate down. And then you do principal component into the separation. With that, you can establish strong photon limits where we have here the Auger limits, hybrid, which is just fluorescence detector with surface detector, only surface detector, which extends to higher energy. And what we see again is that a number of the exotic models that were in fashion at some 20 years ago, for example, topological defects or a Z-burst model, which converts particles late into cosmic rays, or remnants from semi or quasi-stable, very long-lived dark matter, which decays late and then hadronizes, would always be accompanied, like all hadronization process, with neutrino and photon signals. And if you normalize those on the observed cosmic ray spectrum, you would get predictions for photon fluxes, which are those lines here, which are excluded by the limits. So this rules out a lot of the exotic models of ultra-energy cosmic rays and points very clearly to the more conservative astrophysical models that people favor nowadays. As an interlude, we can also look for exotic processes. Here an example, magnetic monopoles. A magnetic monopole, because of the high mass, would just plow through the atmosphere and not lose energy. So it would have a fairly continuous energy deposit as a function of depth in the atmosphere compared to a normal shower, where the shower grows, the number of particles grows, and then at some point the shower can't produce secondary particles, and you observe a decay. So we've done in fluorescence searches for these kind of signals. We don't see them, and this gives Auger the strongest limits, as you can see in the bottom right hand plot, for possible ultra energy cosmic rays monopoles. And it's way below the Parker bound, which is the bound where magnetic monopoles would short circuit magnetic fields in the galaxy. So now to the most difficult part of primary particle identification, which is the separation of protons from ions, or in general at different nuclear groups. The idea behind the techniques is to use the fact that proton has a smaller cross-section in proton-air interactions than iron has in iron-air cross-section. Basically, understandable in the superposition model, an iron is 56 nucleons, so the probability that one of them interacts is higher. Geometrically, one can think it's a bigger wall, so it has a higher interaction cross section, which means, as here illustrated in Monte Carlo simulations, two things. The average shower maximum, if you compare in the top plot and in the bottom plot, is deeper in the atmosphere for protons than it is for ions. But a second observation also, iron, because of the higher cross section, has fewer fluctuations than protons. So it's important we can use both the position of the maximum of the shower and the fluctuations of the maximum of the shower development as variables that are composition sensitive to identify whether we have protons or heavier nuclei as primaries for cosmic rays. And if you look at the superposition height and the Heitler model and elongation, the maximum would always scale with the logarithm of the energy. But in the case of a nucleus, you have to scale this down by the nuclear mass. So now, if we plot the observed average shower maximum and the observed shower Xmax fluctuations and compare them with Monte Carlo simulations with different models where we use as the extremes protons and iron as the simulations to get the limiting lines, you see in the Xmax plot they stay between the two lines, which is good. And you see at lower energies proton dominating, at higher energies you see a turnover to heavier nuclei. You see the same in the plot with the fluctuations, but here you see that the data gets out of the band, so it looks like it wants to have fluctuations that correspond to something lighter than protons, which doesn't make sense for cosmic rays. The interpretation is that we have some problems still with our simulations, not with our data. Here, it's something which does depend on modeling and Monte Carlos to the interpretation. You see here also a band of systematic errors just by seeing how much do the different models vary. And as I mentioned, the observations, especially in the fluctuation part, are not compatible with all the possible models, especially the Sybil 2.1 model here is really very far away from some of the data points. So now you can look at this to see, do we really assume we have pure proton, we have a mix? If you get a mix, you expect more fluctuations because proton showers and ion showers both have the intrinsic fluctuations, but by having the two components in there, you expect even more fluctuations. If you try to fit the signals with a pure composition where you assume that you have a constant mass, then you realize you don't get the fit you would expect, that you have to be here in the 0, but the data is clearly offset from 0. So we have a measure that indicates that we do have, from the spread of Xmax, a non-zero mass. We see this here in a different way of plotting the correlation. Where would we expect if we have pure iron, pure proton, the fluctuations would be below the observed. If we make a 50-50 mix of proton and iron, the fluctuations would be larger. So, which is good news, the observed data point are somewhere in between. Obviously, we're not fitting the exact mix, but it tells us that a mixed composition, by changing those numbers, would allow us to put those lines into the data region. And as I said, it clearly rules out a pure composition, pure iron, pure proton, no matter which model we're trying to use. Another, so there's another observable which can't be fitted just or adjusted only by mixing composition, which is the muon fraction of a signal. If we look at our simulations and compare them with data, we see a fairly good fit for the electromagnetic signal of the fluorescence detector. If we look at the surface detector, where the signal is generated both by electromagnetic and particles and by muons, what we realize is that the data points, the black round circles, are above the simulations, both proton or iron simulations. So if we try to extract the fraction of muons from our models, we have a disagreement, which we can fix by rescaling. But this is a ad hoc fix, not a model fix. So it indicates that the models predict the wrong number of muons. And we can do the similar if we do a rescaling analysis for muons and electromagnetic part. We see the electromagnetic signal is pretty much within the error ellipse. The muon is offset. We see this in both ways of looking at it. So again, we have to rescale the muonic signal. The electromagnetic signal seems to be well reproduced. So this is important. So we have looked at it at a different way to look at asymmetries in our showers. The detectors are sufficiently far apart that the early part of an air shower, which hits the ground before the late part, has some age difference, which means you have more electromagnetic part in the particles in the early than in the late part because of atmospheric absorption. Details are obviously composition dependent, but if you look at the data, you can see very clearly an early late difference in the signals, and you see that the difference is much bigger when you have a more inclined shower of 52 degrees zenith compared to about 15 degrees zenith, where the effect is relatively small. If you're trying to fit the Xmax set of the data you can extract from the models, you realize again here models and data disagree in most cases. So interaction models do need work. And we see this again, and I'm going to talk about a bit more of this because this is again a fairly new result. As part of the infill array, we have, as I mentioned at the very beginning of the talk, the buried muon detectors in the test cell, which allow us to measure muon signals underground directly, where the soil acts as an absorber. And if we look at the muon density versus energy compared to simulation, or with an Xmax analysis, in both cases, again, we see here the signal is barely compatible with iron if we're lucky, but it's systematically above the limiting line that the models would give us. In the other way of plotting it, if we do it with an Xmax analysis, the observed data points are clearly not compatible with any possible composition that we could put. So again, this is another way of indicating that there's something in the models that is not correct. So Auger is really telling us something about that we have to work somehow on our very high energy interaction models. Then one interesting things we've heard about gravitational waves just in the context of neutron stars a moment ago. Auger has done neutrino follow-up for gravitational wave events. These were the first ones which were black hole mergers, nothing seen, nothing expected. So these are basically just slides that prove that we can do this. But then was the famous GW 170817, which was a neutron star merger, which was seen also by Fermis as a gamma ray burst. And because of that, we would expect it that it might emit neutrinos. And for this particular event, if you look at the sensitivity curve, Auger here is the position in the sky of the event. This is our best region of Earth-skimming neutrinos, the tau-induced ones. We were extremely lucky. The event happened in the zone of maximum sensitivity. We didn't see any neutrinos, but we established the strongest limits in the high energy neutrino range. If you look at it in the short 500-second time window, the Auger limits dominate by far. If you go to a 2-week integration period, the Auger limits weaken because the source moves out of our best region. We also know, if you look at the models, that this was not a very energetic event. So the fact that we didn't see anything doesn't mean anything in terms of signs of expected neutrinos, but it clearly establishes that neutrinos are part of the multi-messenger program that we're talking about so much these days. And we have a systematic follow-up for all gravitational wave events to look for neutrinos. And now for something completely different. The Auger Observatory is designed for cosmic rays, but it can do other things too by sheer chance. In this particular case, it turned out that our fluorescence detectors are very good detectors of some of the high energetic lightning events in the upper atmosphere, which are called Elves. This was found by chance by one of the colleagues looking into our detector monitoring data. The triggers wouldn't catch it. We saw signals which, instead of having a signal in our camera which corresponds to a downgoing air shower where you see basically a line in the sky, you get these funny semi-circular blobs evolving in time, early versus the bluish is early, the orangey reddish is late. It took a while first to understand what they were. We had to modify our triggers before people had to dig through data that was not designed for real data analysis to make this up, to construct these kind of images. Now we have a special trigger to detect these kind of Elves events. And we have recently published this in a journal of interest for the atmospheric science community, not for the cosmic ray community. And we can see if we two things here. Those events are very far away. This is a 250-kilometer line. So you can see here is the Auger. By the way, this is the best map where you can locate the Pierre Auger Observatory at the edge of the Andes on the line here between Santiago and Buenos Aires. You see this, most of these events are thunderstorms over the Pampa, some 1,000 kilometers away, which we see. We can determine the location, and they're in good agreement with the determination of locations by the worldwide lightning location network. So this is an interesting extra. So we're using our observatory not only to do high energy cosmic rays, even though this was the main goal, but anything else we can do when we learn about what our telescopes can do, we're trying to add. And in this case, it's quite interesting. Some of the biggest Elves events seen are the ones that Auger can observe. And it's interesting, we see them from below rather than from above, but most of them are seen by satellite instruments. And now for the future, we are working on an upgrade of the observatory. As I pointed out, the composition is difficult to obtain, especially with a surface detector. We're trying to add additional detectors to improve the separation of a muonic and electromagnetic component in each detector to improve the separation between heavy and light nuclei. The determination is that we can really then learn more about the flux suppression, do this combined fit analysis that I showed you before, to see whether what we're seeing as a flux suppression is a GZK cutoff suppression in propagation from including sources far away, or if what we're seeing is simply that even the biggest astrophysical sources don't accelerate particles to much more than 10 to the 19.5, 10 to the 20 electron volts, and they run out of steam at by having higher composition sensitivity, we can try to get a proton enhanced sample. Protons have higher rigidity and therefore smaller deviations of cosmic rays. So this, in the searches like the dipole, a proton would deviate much less in direction compared to a heavier nucleus, and would have a chance to point back to the source, not precisely, not as beautifully, obviously, as in photon astronomy, but at least get sufficiently close to the source that of exotic and high energy sources, there would be only one or a few within an error box.
Excuse me, Lukas, there are 8 minutes left, including time for any questions.
Yes, I'm finishing, thanks. So, and then to study air showers and particle production at the very high energies above LHC energies. So we're improving electronics with higher sampling rates to get more signal details. We're adding scintillator detectors on top of our tanks to get 2-component measurements, which allows us to do electron-muon separation. We have detectors in the field. We've added radio detectors. We have data from prototypes in the field. So this is just showing that our basic design works and we can analyze the data. An interesting thing on top of it is we can detect very inclined radio air showers. We've seen this with the IR detector. And even if we thin it out to a position density, these are the orange dots here that correspond to 1.5 kilometers compared to the very dense air density, allows us to see some signal, which allows us to study very inclined radio events, which would bring an electromagnetic information to very inclined showers, which, as I mentioned earlier in the neutrino section of my presentation, would only have muons on the ground. So it's a complementary information for the surface detector, and we're adding radio antenna to all our 1600 tanks as part of our upgrade program to extend muon and electromagnetic separation tagging abilities also at high energies, high inclinations. So to conclude, just as a summary, Auger has been operating since 2004, but it completed in 2008. It's robust, stable, working continuously. And I've shown you some of the results, the spectrum with the ankle and suppression features, anisotropy, the evidence for a dipole, that we have competitive neutrino limits, that our photon limits rule out some models. Of exotics, I've shown you monopoles. I haven't discussed Lorentz possible limits on violation of Lorentz symmetries. I've shown you different methods of muon counting and assumptions which systematically show a discrepancy with interaction models. I've shown you the gravitational wave follow-up program as part of our multi-messenger program. I didn't talk about the proton-air cross-section measurements for reasons of time. I mentioned briefly some of the non-cosmic ray science with the Elves and talked about the upgrade in progress to extend the science reach. And I would like to mention that just last November, we had our 20 years of groundbreaking at the site. So we're no longer a young observatory, but we're still vital, and we're trying to revive the Auger science with the upgrade. So thank you very much.
And thank you, Lukas. It was fascinating seeing what all is developed in those years and what you have, the research you have going on. I don't know, do we have questions?
Well, there are no questions recorded.
And in that case, if I see that David is still here, was there a question for him that could yet be answered?
Yes, the questions to David have been answered, yes.
They've been answered too, okay.
Yeah, I answered in the question answered session. I wrote, I made my homework.
Very good.
Thank you very much.
Anyway, Lukas, thank you very much for such a terrific talk and description of everything that's going on there at the observatory.
Yes, you're welcome. I was hoping to give this in person. I hope at some point we'll have a chance to have a meeting again, not in virtual, but in face-to-face. And
hope we'll be able to do that next September.
Yeah. Next September, yeah? Next September. Lukas, thank you very much.
This is a must next September.
Yeah.
Greetings to Miriam.
Yes, thanks, Peter.
Yeah, thank you very much.
Well, next we'll move on to today's parallel session discussions. And a couple of the speakers are still missing, but most are here. Just as a reminder for those giving these parallel discussions, you have 3 to 5 minutes to talk about the recorded session that you submitted, and let everybody know what's there and why they should go take a look if they have not done so already. Our first person describing the presentation today will